Great. So let's get started here. And yeah, welcome. So um, we have a few things I want to get to today, and some of that is we have a few more topics to talk about in chapter 11. But then I do want to head over to Excel and see how Excel can help us in some of these processes. Uh, So if you just jumped on, there is an Excel file. It's on Canvas under the Chapter 11 module. So if you want to download that and follow along, feel free. Again, if it's easier for you to watch and then maybe you can pull it up later and verify, that's fine as well. And yeah, so we'll play around in that. So these chapters around testing really do bring back to the forefront Excel as a tool that we can use to speed up our lives and make our lives easier. Okay, so obviously you're being forced to hand churn a bunch of these equations and that's good but once you're familiar with them, we can use a tool like Excel to speed up the process. So we'll look at actually how you might do that in even a production facility scenario. Yeah. So and because of that, so I am going to in the next probably 24 hours there'll be another problem set. So problem set 3 will be posted. It won't be due until next weekend. But it'll have you kind of recreate a little bit of what we're doing here. So I don't anticipate it being anything overly cumbersome, and I'll try to kind of outline very specifically what I want you to do. But I do want you to kind of get your hands dirty and just experience building a testing system in Excel. So yeah, so before we get to that, I do want to talk about one last kind of variation in chapter 11, and in fact we'll turn and do this in Excel in a moment. But that is the dependent samples. So everything we've been working with in chapter 11 and most of the kind of excessive equations that we have to sift through is all under the understanding that we are taking two samples and those samples are not connected in any real way. Okay, so they may be coming from similar populations or what we might be hypothesizing is the same population, but the observations are not connected. So in the dependent, or what we sometimes call the paired t-test, this assumption we now have. So where there's some connection between the observations. So yeah, and that leads us to a much more simplified equation and quite useful process. So that let me just write down the equation or kind of how it fits in. Let's get that blackboard back up. Okay, so get out of the way. Yeah. I'm just checking one last thing. Okay, so when we've made these, we've taken two samples and we've assumed that this is if we've taken a sample of 20, it's a completely different random group of 20. If we're interested in heights across two groups, these are different grabs of people. What the dependent sample allows us to do, or the dependent testing, the paired t-test allows us to do, is contemplate what happens if for instance it's the same person, the same 20 people measured before and after. Okay, height's a little weird, but maybe you measure 20 people at the start of 10th grade, and you measure those same 20 people a year later. Okay, there's information there that, because they're the same 20 people, there's information there that we want to use in our testing. Okay, it's not just another random sample, and in some sense, what we're gleaning is that there's less variation happening, right? We don't have to account for sample 1 being a group of 20 and sample 2 being a whole new group of 20, right? That adds in extra variation, extra jumping around, because that sample can jump all over the sample distribution as well. Whereas when we have this connection between the two, that second group can't jump randomly away from the first group. Hopefully that made a little sense. And so we've captured or removed some of that variation, and we want to take that into account. So actually, let's turn. Well, I'm just going to write down the t-test in this case is very simple looking, okay, and it is as follows. Okay, so it's the difference indicated by d bar, where d bar is just the difference or the distance between, the first sampling and the second sampling of that group. And so this follows a very familiar format, right? There's still a distance or a difference up top and in a form of a standard deviation on the bottom. It's just that we need to, understand where to pull these things from. So let's actually jump over to Excel and see how this makes a difference in our actual calculations. So so as I said, if you just jumped on, there is a file on Canvas under Chapter 11 called Testing Practice. So if you want to pull that up and follow along, feel free. And I'm going to pull it up here at the same time. I think there it is. Okay. Let's get this out of the way. Okay, so probably don't need all of this right now. Just close that up a little bit. Okay, so I'm gonna be working in the 2 sample testing tab here, and what I have are there's 2 samples of what I believe is 20. Yes, so there's 20. Let me turn this on. Follow me a little bit better. So there are 20 observations here. Okay, and we're gonna run a 2 sample test. Okay, and first we're gonna start with the idea that so let's say what was I just talking about? Height. Let's set the height aside. Let's talk about, perhaps these are individuals who think they are concerned about being overweight. Okay, for health reasons, they're concerned and they want to perhaps lose a little weight. And so we have a sample of 20 individuals, and we have 40 individuals, 20 of which we are going to have the control, okay, and 20 individuals we are going to have them have the treatment. Okay, so a very randomized control trial style. We can think of it in this term, and maybe the treatment is they watch a seminar, explaining various dietary changes that they can make. Okay, we can make up the treatment however we want. Maybe it's as simple as a pill, but we have them. We'll go with the video. So they watch an online, as everything is nowadays. They watch an online seminar, and we might be interested in if this produces a change in them. Okay, so we would be working under the hypothesis. Okay, again, we want to set up the null hypothesis. We can just write it out something like, UC is equal to UT. Just do that for ease. We'll not go through the process of inserting the Greek letters. And of course, this means that the alternative is that UC is not equal to UT. Okay, so I'm gonna try to zoom in here a little bit. I realize that's pretty small. Okay, so working with this, if we don't have the assumption of the paired t-test, okay, so we're gonna start back in what we've been working with in the most of chapter 11. what this means is that we're working with, we have to decide, right? We have to decide if we're dealing with a z-test or a t-test. So let's say we don't know the population standard deviation. We're left with the t-test. And then, of course, we have to make one more decision. So what is the, or do we think that the standard deviation is the same across both? Okay, and we could maybe justify that it is, and perhaps we'll, let me try to, yeah. So let's say that it is. Let's say that we can make the justification that sigma 1 is equal to sigma 2. Okay, and we're dealing with people's weights, and maybe that's a reasonable assumption that both of these groups are coming from the same underlying population of people that feel that they're overweight. So our process here, and we'll walk through this and just kind of see Excel helping us out along the way, and eventually we'll turn and do the paired t-test. So let's first, so I've got the mean and the standard deviation calculated for each. Let me freeze some panes here so we can keep seeing what we're doing. And so I have that, you know, our typical average calculations. Let's pull that over. Again, if you have it and you want to follow along, that's fine. If not, you know, you can look at it later. And I'm going to pull over the standard deviation. Now notice I'm using standard dev .s. So this is a sample standard deviation, and we have two different s's here, right? But our underlying assumption is that there is a standard deviation that is true to both of these groups. And again, what the pooled test does is take these two and smush them together to get a good estimate for the underlying, or to get a better estimate of the underlying standard deviation. Okay, we know that there are 20 individuals in each group. I'm using the count A formula just to get familiar with it. That's going to count up how many values or how many cells in here have data or a non-blank. Okay, so we do need we need to figure out what our pooled variance is going to be. And here, let's give myself a little more space. Okay, so I'm just going to kind of you know, work in this area of Excel and not be overly organized with it probably, but the pooled variance, we know from, well, let's just write it down to refresh our minds. Okay, so we have SP squared is N1 minus 1 S1 squared plus N2 minus 1 S2 squared over N1 plus N2 minus 2. Okay, so a pretty gross formula. What I'm actually going to do, and what I often do the first time that I'm typing something out in Excel, is I'll break this up. So I might do top and bottom. I guess we could call it numerator and denominator. And just build that formula, kind of split it up so I don't have as many parentheses to contend with. Okay, so what do we have here? We have N1 minus 1. Right, we can just reference these cells. S1, that's not the right one, so I've already... Don't follow my lead here, that's not good. Do this times the standard deviation squared. Okay, and then we're going to do N2 minus 1. I know I just went off the screen. Times S2 squared. Okay, and that should give us some value. And then on the bottom here, we have N1 plus N2 minus 1. Okay, and now we can smush this back together. Okay, sometimes it's just easier to not keep track of so much, so we'll just finish that off. And we find a pooled variance of 77. Okay, now that seems out of line with our standard deviations. Remember, these standard deviations are standard deviations, so they are the square root of this pooled variance. So one way to double check that your math is done right is to just kind of look at the pooled standard dev, right? Standard deviation, and just take the square root of what we just found, and it should spit out somewhere in between. Okay, and in fact it does. It's a little closer to the second one than I would have imagined. Enough that I might just go in here and verify that I've done this correct. So I can't see my error. If you have found the error, you let me know. This might be right. It just was not exactly what I was expecting. Okay, so we have now we have our Who found it? Who found it? Anybody find it? It was minus 2 down here. And there we go. So I had n, because I wrote this wrong, this is a minus 2. Okay, so I did, let's pretend I did that on purpose just to show you how much these things change with a little adjustment. Okay, so I had the wrong denominator here. And so that altered it. And now that I've got it right, we have a value that feels more in the middle, right? So again, because we have equal sample sizes, I expect this to be roughly in between these two values. And so always good when to kind of verify that you're expecting the result that you get, because this, of course, led me down to finding the error. Good lesson. Glad I did that on purpose. So we have a pooled variance. Okay, this pooled standard deviation we're not going to use. That's just to verify that things look okay. We have our pooled variance, and now we can plug it into the sample, the t-test. Okay, so in Excel there are ways to speed up this process, but I want to see it. I want us to see it kind of in action first here, and then again. We'll get to the paired test here in a second and see how much difference that can make. So the difference, so actually let me just write down, let me get out of the way a little bit. Let me write down the t-test just to remind ourselves. I know we've seen this a number of times, but I can write it on the screen. So this version of the t-test, of course, we're going to look at the difference between these two. And then we're going to use that pooled test, or pooled variance, as follows. Right? And so again, we're going to test and see if this seminar gives enough of a difference. Okay, so we're already kind of into the process of calculating this. Of course, we need to set our alpha, and so let's set it at a typical 5% level. So if we jump over to the t-table, we can find, again, we're at an alpha of 5%, a two-tailed hypothesis test, and our degrees of freedom is going to be at n1 plus n2 minus 2, so in our case is 38, and that leads us to 2.024. Okay, so that's that t-value that we're going to be interested in, the critical value that we're going to pay attention to. Okay. Let's pull back up Excel. Now, we're ready then to go ahead and develop this t-test. Now, let's do this in a couple parts. So the top of the t-test is going to be that difference that. And I already have it plugged in here. So C26 minus C26 minus D26, the difference between the two sample means. Okay, and that is 1.6 pounds. So the treatment the treatment group has a little lower weight. But is that enough evidence? Well, let's plug in the bottom, the denominator of our test. So again, we're working with the pooled variance that we just found. I've hidden it now on you, but pull this back out. So we have that really gross unformatted number here. So let me just clean that up a little bit. We don't need so much. Get a little more readable. And so let's go ahead and plug this in. This is the square root of, my head is in the way of it, but it is SP squared, so the pooled variance, okay, times the following. It's 1 divided by N1, okay, plus 1 divided by N2. Now, obviously, these are the same sample size. We could have smushed that together in this case, but that gives us 2.813 in the denominator, and so our t-value is just the numerator divided by the denominator, and so we get 0.5686. Again, I've got some formatting issues here. I'm just gonna quickly clean that up so we can see things a little bit better. And so we have a t-value. We're comparing that to our 2.024. And so clearly we do not have enough evidence to reject the null. Let's put that somewhere. The value we were interested in is 2.024. Okay, plus or minus, two-tailed situation, but clearly a t-value of just over 0.5 is not enough to reject the null. And so we don't have reason to think that this, the two are not equal. Now, what we're going to do is turn to the paired t-test here in a second. But first, I do want to show you that while it's good to know what's happening here, but Excel does have functions built in to expedite this process. Just going to pull this out a little bit, and if, as you probably can guess, it's over here in the. If I click on the data, there we go. It's over, still hidden. It's in the data analysis tool pack. Okay, there are actually other inbuilt Excel versions as well, but these tend to work even slicker. So the data analysis tool pack. We can go and it has a whole host of them, but what did we just do? We assumed equal variances. Okay, now that's a little small, but there's a two sample assuming equal variances. There is one for the unequal variance, but here this equal variance, so sigma 1 equal to sigma 2, is that pooled test that we just did. Okay, and I have this plugged in here still, but so sample or variable range 1, variable range 2. Now there's some other options here. The hypothesized mean difference of equal to 0. So this two sample testing, we're always kind of so far been setting the two sample or the two population means equal to each other. It is more flexible. We could put in, can we assume that, the treatment group has lost 5 pounds relative to the control or something like that. So it is more flexible. Generally, though, in our case, we'll leave this at 0. I have it set up to put an output down here, and we can set the alpha. Okay, and so when we click OK, again, all we've done is select the groups here. This should spit out some solutions that look like nothing because I'm in the way again. And what do we find? We find it gives us the means. Whoop, I don't want to. Okay, we get we get variances. We're not directly using those, but observations. We get a pooled variance that looks familiar. Okay, we could take the square root of these variances and get our standard deviations. We have our 38 degrees of freedom, and we have our t-stat, which 0.568, 0.568. So that checks out. Again, much easier than what we did the last 15 minutes. And we have various p-values and whatnot, but this does spit out everything we would need to know to determine whether or not we have enough. And actually, this is that 2.024. So we have everything we need right in front of us by just going into the data analysis toolpack. Okay, so now that we know that Excel can do this for us, let's forget about that and let's quickly calculate the paired t-test as well. So a paired t-test is very similar to what we've been doing, but it adds one more element. So thus far in chapter 11, we've been assuming that the two samples we take have no real connection to one another. In that sample 1 is a random selection within a group, and sample 2 is a random selection within a group or a population, right? They're both coming from a population, but there's no connection between the different sampled observations. The paired t-test allows us to take advantage of certain circumstances where we can assume that, or when we know that to be true. For instance, your book outlines, I think they looked at appraisers, and so certain houses getting appraised by more than one appraiser, the observations there are connected by that each appraiser is going to the same house. Okay, so there's information there that we can use. Much of our decision-making process in statistics, we go through a lot of pain to determine which of these specific tests we can use, and that's because we're trying to make sure we don't let go of information. Information is very important and useful, and so if we know something, we try to incorporate that into the test. So paired t-tests are one way that we can do that. Okay, so in our scenario here, so let's say, for instance, I'm going to change what's happening here. So we said we had a treatment and a control, kind of a classic randomized control trial set up, and some of the people went to the seminar. What if instead it was actually before and after, the same people? So what if if the scenario was, this is person and this is 1, 2, 3, let's give them kind of ID numbers. And so really we only have 20 people here, and instead of treatment and control, maybe we've done before and after, right? So maybe we did they weighed themselves before going to the seminar, and then they went, and then it was a month later, and so we can determine whether or not they've lost weight. So to use that information, we're going to connect these observations. So person 1 is, we're gonna smush together the information from person 1, and we're gonna simply consider this a difference. Okay, we could think of it as the weight loss, and this is it's not going to matter which one we put first, but this person lost 19 pounds. Okay, so it's not two random people who just happen to be at the top of our list. This is the same person. So we can drag that down. Some people gained weight, some people lost weight. The positive numbers here are losing weight. Maybe it makes more sense to flip that around. I don't know. The end result won't change. Okay, now let's just look at this a little bit. Let's see. So, well, we can just do it right down here. So what's the average of this column? You may be able to guess what this is going to be. It's 1.6. Okay, so the average difference is the difference of the averages, right? So we had that down here at 1.6, and of course, the average of the differences is that. So, so we're not changing anything about the differences, really. What we are changing is the standard deviation. Okay, so the standard deviation here, let's pull this across. We're going to have a different standard deviation. In this case, it's just under 13. And so, but now we're not going to use both standard deviations. Okay, so we're actually going to we're going to plug this together and build. So n is also going to be n is also going to be 20. So now we have what we need to create the paired t-test. Now I'm gonna just write that up here. Again, it's obviously in your text, but the t-test we're going to use here is, we refer to this as kind of a d bar here, where it's the difference. Okay, so it's still going to be a difference between two things, except in this case it's connected to the observation. So we just take the average of the differences between each person. Again, as we just saw, this is still going to be 1.6. And then on the bottom, we're back to a more simplified version where we're just looking at the standard deviation of those differences divided by the square root of n. Okay, but same thing. The bottom here is still talking about how much does that top tend to move around. Okay, same concept as we've been working with for a couple chapters now. And so we're ready to plug that in. Okay, I have it kind of written out here with avoiding spending the time to plug in the Greek letters. But the difference here again is going to be, you can just pull it straight from there, 1.6, and then the bottom is that standard deviation divided by the square root of n. Okay, and we get 2.9. And lastly, so let's just throw this together. Now, nothing's going to be wildly different. In this case, the t value is 0.552. When we didn't pair them, we ended up with 0.5686. Okay, and so they're very similar. In this case, it's a little bit smaller. It can go kind of either way. Again, much of what we're doing here, whether it's determining, you know, z versus t versus which of the t's pooled or unpooled versus the paired, none of this drastically changes the underlying fundamentals, which are driven by our samples, right? So our sample numbers here are not changing. These weights are not changing. What we're changing is some of the assumptions about the relationship between these, in this case, the relationship between the two samples. In the t determinations, we're talking about you know, whether the standard deviations underneath are the same. Again, that's not changing the large important values here. It's just tweaking a little bit in terms of what can we glean from this scenario. So we should never expect wild swings, you know, in our t values. And much like, you know, my purposeful error earlier, if we do see drastic changes, we may have calculated something wrong. Similar to what we showed before, let's pull this over. We can let Excel do this for us again. So let me go back up to my data analysis, and I'm going to now pick paired two sample test for means, or paired two sample for means. It's a t-test. And again, we'll plug in those values. I think I have them already selected, but we just drag those. Again, assuming no difference, and an alpha of 0.05. And where is this going to spit out? Up there. That seems fine. Let's go ahead and click it, and we get again what we should probably expect. So here's the means. The variances still coming with observations. Notice degrees of freedom is that 19. So we didn't go back to the t table, but that's a different cutoff. So it's a little bit larger of a cutoff than we had with our pooled version down here. Okay, so we do need to recalculate the degrees of freedom, and I didn't mention that, but degrees of freedom for the paired t-test is simply n minus 1, because we only really have a sample size of 20, right? We just have each person showing up twice, but our sample now really is just these differences. So our sample size is 20 differences. And what do we get? We get a t-stat of 0.5516, which rounded here, we get the same thing. Yeah, so this is that critical value, a little bit larger than we showed down here, which we should expect, right? So a degrees of freedom down to 19 makes it a little wider. We got to add in a little more uncertainty. But so here, this is Excel doing that for us. As you may have noticed, we have the other versions down here. So a 2 sample, we've done the equal variance, the unequal, so that's going to not pool them together. This can be helpful. This would give you that degrees of freedom without having to do the gross calculation. And then, of course, we have the Z test as well. Okay, so as you can see, we're as we started the data analysis tool pack way back when, we first touched on descriptive statistics, histograms, things like that, and a lot of the stuff we weren't sure of, we're starting to pick these off quite quickly. Okay, so a lot of this stuff you'll at least be somewhat familiar with, and we will touch on correlation, covariance, regression here in the next couple weeks. So let's move over to the production sampling testing and take a look at what's there on that sheet. So what I have shown here, or what I want to walk through, is how can we use Excel to speed up our process in our verification process or our testing of samples. Maybe in this case, in like a production process or a assembly line where we're going to sample some of our product, but this can be broader context. We could use it for verifying that things are going well with our quality control or our salespeople and their sales calls. Whatever we can take a sample of, this can be applied, and using Excel to shortcut some of these equations and repetitive processes. So so the way I have kind of the situation set up is, let's imagine we're going to take a sample every day or so. And we're going to sample, I think I have it set up for 30. So we're going to take a sample of 30 of our product. Okay, so maybe we're making, I don't know what would be 12 inches or 12, that's a foot. We're making hot dogs. We're making foot-long hot dogs. Okay, and we want them to be a foot long. Okay, I don't know if foot-longs are actually a foot long, but let's go with it. That's our marketing model, that they are, in fact, a foot long. And so we're going to test whether or not that's true by sampling 30 hot dogs. You can choose to eat them afterwards or not, but we're going to sample 30 hot dogs and verify that production's going well. Okay, now so our null hypothesis is that the mean is 12. Alternative is that it's not, right? We would care if it's too small or too long. We're going to use a 0.05. We could change that. So this is going to be helpful in one of the cases. So let's say that the manufacturer that made the part of the machine that cuts it at 12 inches, whatever part of the process that is. It's been a long time since I've been in a meat packing plant. And we have the hypothesized mean is 12. Okay, so anyway, that production process has suggested or told us that yes, the population standard deviation is 0.21 inches. We may use that or we may not, but let's say that they've claimed that. Now, what we have set up is, let's say we take a sample and we get our 30 lengths of our hot dogs. We can have Excel do the average, the standard deviation. We know N is 30. I'm using the count A here just to get in that habit of an easy way to count up how many non-blank entries are there. And so what I have set up is something where we can quickly determine whether or not we're within the limits that we've set on ourselves. Okay, so let's calculate those control limits, or those critical values of which we're concerned about if the mean is within. Okay, and so in some sense you can think about now having taken a statistics course, you can grasp these concepts. You may be working with people down the road that don't have a statistics background. So how can you set up the process so that they don't have to go ahead and be able to calculate t-values? You can do this kind of in advance for them. So we can look up, so we need to find that t critical value, right? And so Excel has some tools for this. So there's something called the t inverse, or the inverse t function. Okay, and there's one for each side of the tails, and then this is the two-tail. So t.inverse.2t is a two-tailed, and it's going to spit out the t value that gives us whatever percent we're interested in. Okay, so let me walk through that again. So it's going to ask for, if you can see that it's kind of small, when I type in t.inv.2t, it asks for a probability and a degrees of freedom. Okay, so it asks for a probability, which we're going to plug in our alpha. So we're asking Excel, okay, I have a t distribution, and I want you to tell me what t value means that only 5% are on the outside. Okay, and that's what it's going to spit out. And of course, I do need to give it a degrees of freedom because that t distribution changes depending on our degrees of freedom. So I plugged in, our sample size -1 and that 5%, and it's going to give me 2.045, right? And so that's going to change. Just to highlight that that's going to change when I change this alpha up here. I think I have the setup that if I go to 0.1, it's going to change it down to 1.69. Right, so as expected, and you can use this inverse for anything, any value. Okay, so let's put that back at the 0.05. So we know the t value that we're going to be interested in is 2.45. Now we could stop there, but again, part of why we're going through this is to remove that necessary statistical understanding for some of our maybe coworkers. Okay, so let's take it a little step further. Let's put it in terms of what sample mean do we need to think about? Okay, so when we get a sample mean back, is that concerning or not? So we can use the let's say we'll go with the standard deviation that they've given us. Okay, so we're going to set this up so that to do as little work for our coworkers as possible. The other way around, so they have as least to do. Sample size of 30, and so that means we can kind of put together a standard error of the mean. Again, this is not quite exactly what we've been doing because we're using that population standard deviation in a t equation, but for this purpose, for kind of verifying, this is probably an all right kind of thing to do. Okay, so that gives us kind of the bottom of the t value, hypothesized mean, and so what we can do is build those control limits. So basically, we're undoing the standardized equation, right? So we're taking, okay. So what is this doing? This is the mean 12. Now, how far away from that mean can I be in inches? Well, I can be plus that t value 2.045 times that kind of standardized movement, the standard error. I can be that far above, so that's what this control limit does, or this lower one, the lower control limit, does that but with below. Okay, so there's a minus in there. So that sets up two parameters that your coworker plugs in sample of 1. It auto fills into here, right? We could set it up so that it auto fills, and they see, okay, so I got a sample mean of 11.959, and that's in between these two values, so I'm okay. The process is running fine. Okay, so you've done all of the work in the background, and they're able to just glance, see the sample mean, and so on. And so we can, so you can imagine, we have this set up. I'm gonna unhide. I have some already kind of pre-done, and so let's say sample 2, 3, and 4. The next 3 days go on. And again, we could have this pre-set up, so I'm going to unhide some. And the second sample day spits out 12.029, which is within this boundary for our critical values. Third day, all of a sudden, it's outside. Okay, so your coworker has just plugged in these samples, right? They've just typed in whatever size they were. And now they can notice that that's outside of the critical value, and that also in day 4, it's above. And so in both of these days, we want to kind of red flag that and stop and dig deeper into it. Okay, so a way that we can take what we've been learning here and use Excel to kind of speed up the process, and especially for these kind of repetitive sampling scenarios. So we could take this one step further. Let's say you don't trust your coworker at all to even do the mean calculation. So we can have that, or really to compare the mean to the control limits. Okay, so let's go down here. I'm just scrolling down. I have it set up slightly different, and this is going to take it one step further. So let me just hide these so it's, again, kind of back to first sample. We're going to go ahead and calculate the p-value. So this is the difference between what we got as a sample mean. I'm still pulling from up here. You could probably rework it and put it down there, but we know that there's a difference. We were off. That sample was off 0.041 from our hypothesized mean. We have a standard error of the mean. Again, now we can pull from that sample standard deviation and the sample size, and then we put that together. Well, first we have degrees of freedom, but we put that together into the t-test statistic. We get a t-test statistic of a little under 1.0, negative 1.0. And we can put that into a p-value. Okay, so this is the t.dist.2t function. So it's kind of the reverse of that inverse. Okay, so it's the verse of the inverse, whatever. It's the original of which the inverse was the inverse of. This is the t.dist wants an x and it wants degrees of freedom, right? We're in t world. We needed degrees of freedom. We plug that in. And we plug in the x, so that t value. So it's going to take the t value, in this case negative 1.027, and say how likely is it that we would get something beyond that. And what we find is that that would happen about 31% of the time. Okay, that fits pretty close to our empirical rule, right? I know we're in t world, but not wildly different. Now, the only other thing to note here is that Excel, the two-tailed test, does not like negative numbers. So I'm actually using an absolute value function in here, which is grabbing that negative 1.027 and changing it into a positive. Again, that doesn't matter when we're thinking about two-tailed, because the odds of getting something beyond, really that two-tailed is measuring in both directions. So it doesn't matter if we plug in positive or negative. So just something to note when you're building that. There might be an easier workaround nowadays, but if there is, I'm unaware of it right now. And then lastly, let's dumb it down fully for your coworker, right? You really don't trust them, so we're gonna just give them a big button that turns green if things are okay, right? So now all they need to do is type in these 30 observations, and so I have this set up to say if this p-value is less than 0.05, so the alpha, I think I have that up here. Okay, if that's less than 0.05, then do something. If not, do something else, right? So this is an if statement, and so because it's not less than that, it's going to go with the second value there and say okay. But now we have this set up to do the next few days. Day 2 we said was fine. Day 3 and day 4 had problems, right? They had problems up above. They were outside of that critical value. They're in the rejection region. Similarly down here, they're in the rejection region, and we just have, we could maybe set this up to flash right at them, and they need to shut down and verify what's happening. Okay, so again, a pretty easy process to set up to speed up this process. You don't have to run a t-test. You don't have to sit and handwrite a t-test every time. You simply, drag. We can set it up for the next 3 days. Obviously, we don't have data. We could set up both of these for the next 3 days. Again, we'd probably want the actual sample data we could put in, somewhere else. We get the new samples. Obviously not of those hot dogs, or something's wildly wrong. And we get the following. Okay, so it definitely got angry at me. Something's not pulling over correctly because I started typing randomly. Oh, I only did 1 day. That's why. So I've done the next day, and of course we need to shut down. Okay, so you can see that all it takes now is to enter in that new data, and we get the red button flashing. Okay, so that's really what I want to highlight to you. Again, we're not going to become experts in Excel in a few weeks, but hopefully these types of concepts have seen not only the statistics done by hand, but how we can apply that to a real world situation and use a program like Excel to make our lives a lot easier, right? So we're forcing you to go through a lot of these by hand, but that is because you can't sit down to Excel and formulate this if you don't understand what formulas you want to build. So it's kind of both need to work together. So I think we'll leave it there. I will have you get a little bit of practice with this in the next week or so. In the next day or so, problem set will be posted kind of touching on this stuff, and I'll give you some good direction as to what exactly I want you to build, but some sense of this type of let's take what we've been learning in these sample testing chapters and have Excel do it for us, because again, this is a pretty handy way to use a package like Excel. So look for that, and then we'll pick up from there, and we'll start into regression next week.